Okay, so get this. What if everything we thought we knew about, like, the universe's building blocks was just part of the story?
Hmm.
You're ready to have your mind blown.
Always.
Because today, we're diving into some seriously wild physics.
Well, let's do it.
We're talking about the possibility of a whole new type of particle,
Okay.
a paraparticle.
Interesting.
And get this, it could rewrite our understanding of, well, pretty much everything.
Yeah, this is some pretty groundbreaking stuff.
But before we get ahead of ourselves,
Right.
let's do a quick recap of what we thought we knew about particles.
Of course. So for decades, our model has been based on two fundamental types,
Okay.
fermions and bosons.
Right, the classic duo.
Exactly. Fermions, like electrons, are the matter particles.
Yeah.
They're bound by the Pauli exclusion principle, meaning they can't share the same quantum state.
So each electron needs its own unique spot, so to speak.
Exactly. Now, bosons, on the other hand, are the force carriers, like photons.
Okay.
They're much more social. They can occupy the same state, which is what gives rise to phenomena like light waves.
Okay, that's a good refresher. So we've got our fermions, our bosons.
Yeah.
Everything's neat and tidy.
Right.
But from what I've read, this new research is suggesting there might be something beyond just fermions and bosons.
Precisely. This is where things get really interesting.
Okay, I'm all ears.
Researchers at Rice University are exploring the idea of paraparticles.
Paraparticles.
And the name itself kind of hints at their nature existing alongside or beyond our current framework.
So how do these paraparticles fit into the picture? I mean, where do these new guys slot in?
Well, the key lies in how we describe particle behavior mathematically using something called wave functions.
Okay.
So imagine swapping two identical particles.
Right.
The wave function tells you how they'll behave. With bosons, you get a value of +1.
Oh, yeah.
With fermions, it's -1.
Positive for bosons, negative for fermions.
Got it.
But I'm guessing paraparticles don't quite follow these rules.
You're catching on quickly. The innovation from the Rice team is that they're using matrices instead of simple numbers in their wave functions.
Matrices. Okay, now we're getting into some serious math.
Yeah, it gets a bit complex, but bear with me. These matrices still square to the identity, but they allow for values between +1 and -1.
Whoa, hold on. So instead of just being on or off like a light switch, we're talking about a dimmer switch that can exist at any point along the spectrum.
That's a good analogy. But it's important to remember that even with a dimmel switch, you're still ultimately dealing with a single light source.
Right.
With paraparticles, it's more like having multiple light sources that can interact and influence each other in complex ways.
Okay, so it's a more nuanced dynamic situation than just a simple in-between state.
Yeah.
But what does that actually mean for how these particles behave?
It means they exhibit properties of both fermions and bosons,
Wow.
but not fully either. They don't strictly obey the exclusion principle, so they can sometimes occupy the same state. But they also can't completely overlap like bosons. It's a fascinating middle ground.
So to use another analogy, it's like they're blending the rules of two different games.
Yeah.
Like sometimes they play by basketball rules, sometimes by soccer rules, but never fully committing to either.
I like that. It captures the idea that they're not simply a hybrid of fermions and bosons, but something truly unique with its own set of behaviors.
This is blowing my mind wide open.
Yeah.
Does this mean there could be all sorts of matter and phenomena out there that we haven't even conceived of yet?
That's precisely the excitement surrounding this research.
Oh, wow.
It opens up a whole new realm of possibilities, a vast uncharted territory in the landscape of physics. But the question remains, where do we actually find these elusive paraparticles?
Right. It's one thing to theorize about them, but another entirely to prove they actually exist. So where should we be looking?
Well, the research suggests two main avenues. The first is that they might exist as what are called quasi-particles.
Okay, I'm intrigued. Break that down for me. What's a quasi-particle, and how is it different from a regular particle?
Think of it this way. A regular particle is like a solo musician, while a quasi-particle is like an entire orchestra.
Okay.
It's not a fundamental particle itself, but rather a collective behavior within a material.
So like a group of particles acting together in a way that mimics the properties of a single unique particle.
Exactly.
Give me a real-world example so I can wrap my head around this.
Sure. Think about sound waves. They aren't individual particles, but rather a collective excitation of atoms in a material. Paraparticles could manifest in a similar way, arising from the complex interactions of particles within certain materials.
Wow, that's really cool. But I hear there's an even more mind-bending possibility.
Right.
Tell me about that.
The even wilder possibility is that paraparticles exist as elementary particles, the fundamental building blocks of the universe.
Okay, now we're talking.
Yeah.
And this is where dark matter comes into play, right?
Yeah.
This mysterious stuff that makes up a huge chunk of the universe, but we can't directly observe.
Exactly. Paraparticles with their unique properties could be a key piece of that puzzle, potentially explaining how dark matter interacts with the universe in ways we haven't been able to detect.
This is getting seriously exciting.
Uh-huh.
So we've got these potentially game-changing particles that could revolutionize our understanding of dark matter and who knows what else. But there's always a but in science, isn't there?
Of course. As exciting as this is, it's crucial to remember that mathematical possibility doesn't automatically equal existence in nature. Just because we can model something doesn't mean it's actually out there.
All right, back to reality. I appreciate that reminder. Can you give me an example of where the math works out but the particle doesn't seem to exist?
Take, for instance, particles with a spin of 17.5. Perfectly valid mathematically, but we've never observed anything like it in the real world.
Okay, that makes sense. So how do we go from these fascinating mathematical models to actually finding paraparticles if they're out there? What's the next step in this scientific detective story?
It's going to require some seriously clever detective work and some very specialized tools. We might need to look at extreme environments like the early universe or the cores of stars to see if we can find any evidence of their existence.
That sounds like quite the challenge. Yeah. We're not talking about something we can just whip up in a lab, are we?
Definitely not a simple task. Creating the conditions to potentially observe paraparticles would likely push the boundaries of our current experimental capabilities. But the potential payoff is immense. Think about it. We might be on the verge of discovering a whole new category of particles.
That's a pretty enticing prospect. But I'm also curious about what this could mean for us here on Earth. Beyond the mind-blowing implications for cosmology, are there any practical applications for these paraparticles?
That's a great question, and one we'll dive into more deeply in the next part of our deep dive. Stay tuned. So we've established that paraparticles could really shake up our understanding of the universe at a fundamental level.
Yeah, it's pretty mind-blowing stuff.
But let's shift gears for a moment and bring this back down to Earth.
Right. Let's talk about so what factor? What could this potentially mean for our everyday lives?
Okay.
Could we be looking at flying cars or teleportation devices powered by paraparticles?
Well, maybe not flying cars just yet. But the potential applications are definitely exciting.
Like what?
One area where paraparticles could have a huge impact is in the field of quantum computing.
Okay, color me intrigued. I've heard a lot of buzz about quantum computing, but it always seems so futuristic.
Yeah.
How could these paraparticles change the game?
To understand that, let's back up a bit.
Okay.
Traditional computers rely on bits,
Right.
which can be either a 0 or a 1.
Uh-huh.
Quantum computers use qubits, which can be in a superposition of states,
Okay.
both 0 and 1 simultaneously.
Right. That's what gives quantum computers their incredible processing power. They can explore multiple possibilities at the same time. But how do paraparticles fit into this?
Well, imagine if we could create qubits based on paraparticles.
Okay.
Because they can exist in this ambiguous state, not quite fermion or boson. They could potentially perform calculations in ways that are impossible for traditional qubits.
So we're talking about potentially unlocking new levels of computational power that could revolutionize everything from drug discovery to material science.
Exactly. And it's not just quantum computing. Paraparticles could also lead to the development of new materials with unheard of properties. Imagine materials that can conduct electricity with 0 resistance or exhibit completely novel optical properties.
This is mind-blowing stuff. It sounds like we're talking about a technological revolution on par with the invention of the transistor or the internet.
It's certainly a possibility. And beyond these tangible applications, there's the deeper impact on our understanding of the universe itself. Imagine a world where we can finally solve the mystery of dark matter or gain a more profound understanding of the fundamental forces that govern reality.
It's enough to make your head spin. But as you said earlier, we need to balance our enthusiasm with a healthy dose of scientific caution. Just because something is theoretically possible doesn't mean it's easy to achieve, right?
Absolutely. We're still very much in the early stages of understanding paraparticles. There are immense challenges ahead, both in terms of experimental verification and in harnessing their potential for practical applications.
So what are some of the biggest hurdles researchers are facing in this quest to unlock the secrets of paraparticles?
One of the biggest challenges is simply detecting these particles if they do indeed exist as elementary particles.
Right.
They might only manifest under very specific extreme conditions that are difficult to replicate in a laboratory setting.
So we're talking about potentially needing to create mini black holes in the lab or simulate the conditions of the early universe. That doesn't sound easy.
It's definitely not a walk in the park. It will require pushing the boundaries of experimental physics, developing new techniques and technologies that allow us to probe the universe at unprecedented levels of detail.
So it sounds like we're in for a long and potentially frustrating journey. Are there any specific experiments or research avenues that hold the most promise for shedding light on these elusive particles?
One promising approach is to look for the subtle effects that paraparticles might have on other systems. Even if we can't directly observe them, their presence could leave behind telltale signs in the way other particles behave.
So it's like looking for the footprints of a creature we've never actually seen, but we know it must be out there somewhere.
That's a great way to put it. And these footprints could be anything from unexpected energy signatures in particle collisions to subtle variations in the properties of certain materials.
Okay, I'm starting to get a sense of the scope of the challenge here. It's not just about building bigger and better particle accelerators, but also about developing new ways of thinking and interpreting data.
Exactly. It will require a combination of ingenuity, persistence, and a willingness to embrace the unexpected.
Well, that sounds like the perfect recipe for a scientific breakthrough. But I'm also curious about the potential pitfalls. What are some of the things that could go wrong in this search for paraparticles?
One risk is that we might misinterpret our observations. The universe is full of surprises, and what we think is evidence of paraparticles could turn out to be something else entirely.
So there's a chance we could go down a rabbit hole chasing a phantom particle that doesn't actually exist.
That's always a possibility in scientific exploration. But even if we don't find exactly what we're looking for, the journey itself can lead to valuable insights and unexpected discoveries.
That's the beauty of science, isn't it? It's not always about finding the answers, but about asking the right questions and being open to the unknown.
Precisely. And who knows, maybe the most fascinating discoveries are the ones we haven't even imagined yet.
I like that optimistic outlook. Sounds like we're in for quite a ride as we delve deeper into the world of paraparticles.
Indeed. But before we get too carried away with speculation, let's take a step back and recap what we've learned so far about these mysterious particles and their potential impact on our understanding of the universe.
That sounds like a good plan. I'm ready to synthesize all this mind-blowing information before we venture further into the unknown. All right, my brain is officially full, like we've covered so much ground in this deep dive.
It's a lot to take in, isn't it?
From the theoretical foundations of paraparticles to their potential applications, and like the daunting challenges of even proving they exist.
Right. And we've barely scratched the surface of this whole topic.
It really makes you appreciate how much we've learned, but also how much we don't know.
Absolutely.
I mean, a century ago, we didn't even know about dark matter.
Yeah.
And now we're talking about potentially discovering a whole new type of particle that could rewrite the rules of physics as we know them.
It's a testament to the power of human curiosity.
Totally.
And our, relentless pursuit of knowledge.
It's both exhilarating and a little bit daunting, wouldn't you say? It's like we're standing at the edge of an uncharted territory.
Absolutely.
With infinite possibilities stretching out before us.
It is a humbling experience for sure, but it's also incredibly inspiring.
I agree.
It reminds us that there's always more to learn, more to discover, more to wonder about.
So as we wrap up our deep dive into the world of paraparticles, let's circle back to where we started and summarize the key takeaways for our listeners.
Okay, so first and foremost, paraparticles are a theoretical concept that challenges our existing model of particle physics. They have the potential to revolutionize our understanding of the universe, from the smallest subatomic particles to the largest cosmic structures.
Exactly. And we talked about two main possibilities for their existence.
Right.
Either as quasi-particles, which are collective behaviors within materials, or as elementary particles, the fundamental building blocks of the universe.
And the implications are huge. If paraparticles do exist as elementary particles, they could hold the key to solving some of the biggest mysteries in physics.
Right, like dark matter.
Exactly. The nature of dark matter, the origin of the universe itself.
But we also need to acknowledge the challenges.
Of course.
Detecting these particles, if they exist, will require pushing the boundaries of experimental physics and developing new technologies and techniques.
It's a long and potentially arduous journey, but the potential rewards are so great that it's a challenge worth pursuing.
I think that's a great point to end on. So to our listeners out there, keep those minds curious and keep exploring the vast and wondrous universe we call home.
And never stop asking questions.